You know where the ibex will cross tomorrow. The place is 2 valleys away. To reach it, the hunters must follow the river until it splits. Take the narrower branch, pass a marsh on the left, climb through a gap between 2 ridges, and wait below a steep mountain where the animals descend at dawn. There is one problem. You cannot go with them. Your ankle is swollen badly enough that you can barely stand. So, 20 people who have never made the journey must somehow carry the route without carrying you. You can describe it. Follow the river, turn near the dark rock, keep the marsh on your left. But left changes when a person turns around. A ridge that looks obvious from one side disappears from another. A river can divide twice, and if the hunters choose the wrong branch, they may lose an entire day before they realize the mistake. You could climb somewhere high and point. But no hill lets you see the whole journey at once. The valley bends behind mountains, the river disappears into trees, the destination lies beyond the horizon. No human being has ever stood above this entire landscape and looked straight down at it. Yet somehow you need to show all of it at the same time. So you pick up a flat stone. One groove becomes the river. A fork becomes the tributary. 2 rising lines become the ridges. A cluster of marks becomes the marsh. And one shape near the edge means the animals are here. The stone does not look like the landscape. It cannot. The mountain is not flat. The river is not a scratch. The distance between 2 marks may not match the distance your legs must walk. But another person can point at the stone and understand a relationship that exists somewhere else. That is the strange problem behind the invention of maps. Humans did not need to learn how to draw the world from above. They needed to learn how to detach space from the person moving through it. A route normally exists as a sequence inside a body: walk forward, turn, climb, cross, remember. A map does something radically different. It makes all those places exist together. The real invention was not the bird's eye view. It was portable spatial memory. And the oldest evidence may come from people who needed that memory for exactly the kind of problem you are facing, finding a way through a landscape large enough to hide itself. For most of human history, landscapes did not need to be drawn to be known. They lived inside people. A skilled hunter could remember the sequence of waterholes across a dry region. A fisher could recognize where a current changed by the feel of the boat. A child could learn that a certain ridge should remain on one side during a journey, that a particular tree meant a crossing was close, or that an unusual rock marked the point where 2 routes separated. This is spatial knowledge without cartography, and it can be extraordinarily precise. The weakness appears when the person carrying that knowledge is absent or dead, or trying to explain a route to someone who has never walked it. Spoken directions are usually tied to movement. Walk until you reach the river, turn toward the sunrise, continue until the mountain appears. These instructions are powerful because they tell a traveler what to do next, but they do not easily show how the river, mountain camp, marsh, and hunting ground relate to one another as a whole. A map changes the grammar of space. Instead of asking, "What do I do after I reach the river?" it allows a different question. Where is the river compared with everything else? That sounds obvious because modern people grow up surrounded by maps, road maps, transit diagrams, weather maps, floor plans, video game mini-maps. The phone in your hand constantly shows a tiny version of a world you could never see from that angle. But the mental move is strange. To make a map, humans have to ignore much of what a place actually looks like. A mountain becomes a mark. A 3-day walk becomes a distance on a surface. A river that curves through depth becomes a line. The mapmaker must decide what matters and throw almost everything else away. Color may disappear. Smell disappears. Slope may disappear. The sound of water disappears. The difficulty of the walk may disappear. What remains is relationship. This place connects to that place. This feature lies beyond that one. This route passes between those two. That is why the first map may not have looked like what a modern viewer expects. It may have looked like meaningless scratches. Archaeologists face the same problem in reverse. When they find a prehistoric engraved stone, they cannot simply ask whether the image resembles a modern map. They have to ask whether the marks preserve relationships found in a real landscape. In one cave in northern Spain, a group of researchers believed they found exactly that. Abauntz Cave lies in Navarra in northern Spain. Inside it, archaeologists recovered an engraved stone block from a late Magdalenian layer dated to about 13660 calibrated years before present. The block is small enough to hold. Its surface is crowded. Animals overlap with lines. Curves cross other curves. Some marks are deep, others are faint. Nothing announces this is a map. Pilar Utrilla and her colleagues spent years examining the engravings and comparing them with the terrain outside the cave. Then a pattern began to emerge. Across the upper part of the stone, they identified a meandering line that could correspond to a river. Two smaller lines appeared to join it like tributaries. Near them were shapes the researchers interpreted as mountains. One of those forms, they argued, resembles the mountain visible from the cave itself. Ibex were engraved near the slopes. Elsewhere on the block were repeated curving bundles of lines that could represent ponds, flooded areas, routes, or access paths through the surrounding geography. The team published its interpretation in the Journal of Human Evolution in 2009. Their argument was careful. The block could be a sketch of the local landscape. It might have helped plan a hunt, or it might have preserved the story of one that had already happened. That uncertainty is important. No label beside the river, says River. No prehistoric hunter left a note explaining the legend. But the case becomes interesting because individual marks are not the strongest evidence. Their relationships are. A river bends in a particular direction. Tributaries join near mountains. Animals appear in places that make ecological sense. The cave itself occupies a strategic gorge inside the landscape being proposed. The stone may therefore preserve something more than an animal scene. It may preserve a spatial argument: if you are here, the water runs there, the mountain rises there, and the ibex move through this zone. If that interpretation is correct, the block is remarkable not because someone somehow imagined a view from the clouds. They did not need to. They could construct the larger landscape piece by piece. Walk one valley, remember the bend, cross another, remember the ridge, return to the cave. Then compress those experiences onto one surface. A map can be assembled from journeys that no one ever sees simultaneously. But this creates a dangerous archaeological temptation. Once you start looking for maps, almost any geometric image can begin to look like one. And one of the most famous candidates for the world's earliest map demonstrates exactly why that is a problem. At Çatalhöyük, in central Anatolia, archaeologist James Mellard excavated a Neolithic wall painting dating to around 6,600 BCE. Its lower section contains a dense geometric pattern. Above it sits a large spotted form with two prominent peaks. Mellard proposed an extraordinary interpretation. The shapes below were buildings seen from above. The double-peaked form was Hasan Dağı, a volcano roughly 130 kilometers away, erupting behind the settlement. If so, the painting could be an extremely early town map combined with a landscape scene. The idea became famous. It also became controversial. Archaeologist Stephanie Meese later re-examined the image in the context of other Çatalhöyük art. She argued that the supposed volcano could instead be a leopard skin, an animal motif common at the site, while the supposed buildings could simply be a geometric design. Then geology complicated the debate again. In 2014, Axel Schmidt and colleagues dated volcanic material from Hasan Dağı and found evidence for a Holocene eruption whose age overlaps with the period in which the mural was made. That makes it plausible that people in the region could have witnessed an eruption. But it does not prove that this particular painting is a map. That distinction matters. Evidence that the volcano erupted is not evidence that every double-peaked shape represents the volcano. This is where the invention of mapping becomes clearer. A map is not defined by looking map-like. It is defined by a system of correspondence. The marks must stand for spatial relationships in some repeatable way. This line means a coast. This gap means a pass. This point means a settlement. This distance means something about another distance. Without shared correspondence, an image may be art, memory, ritual, decoration, storytelling, or something modern viewers no longer know how to classify. So, the crucial breakthrough was not drawing recognizable objects. Humans had been doing that much earlier. The breakthrough was agreeing that marks could stand for places according to rules. Once those rules existed, a map could become less realistic and more useful. A perfectly drawn mountain may tell you what the mountain looks like. A triangle placed correctly between two rivers may tell you how to reach it. Cartography begins when spatial relationship becomes more important than visual resemblance. And once societies settled, owned fields, built canals, and taxed land, those relationships stopped being merely useful. They became something people could argue over. Where exactly does your field end? Which river lies beyond it? What belongs inside the boundary? At that point, a map was no longer only memory. It could become evidence. In ancient Mesopotamia, maps appear on clay. One of the oldest known examples of a regional topographic map comes from the area of Gasur, later called Nuzi, in what is now northern Iraq. The tablet dates to the middle of the 3rd millennium BCE, around the 24th century. It is only a few centimeters across, yet its marks represent a landscape far larger than the object that carries them. Mountains are shown along the edges. A river runs through the middle. Other watercourses join it. Circles appear to represent settlements. Even more important, cardinal directions are marked. That last feature solves a problem your injured hunter at the beginning still had. A route described through your body changes when your body turns. Left becomes right. Forward becomes backward. But north does not care which way you are facing. Once a map can be oriented to directions outside the body space becomes stable. The map is no longer saying, turn this way from where I am standing. It is saying these places retain these relationships regardless of who holds the tablet. That is a profound change. A shared orientation allows two people who never travel together to refer to the same space. It also allows measurements to become comparable. Fields can be recorded, canals can be planned, territories can be divided. Mesopotamian scribes produced plans of buildings and fields as well as larger maps. The reason is easy to understand. Agriculture turns space into property. Irrigation turns water into infrastructure. Cities turn land into administration. If one family claims that a boundary lies beside a canal, and another family claims it lies 50 steps farther east, memory alone may no longer be enough. A durable spatial record can support authority, but a small regional map still depends heavily on local knowledge. A person familiar with the landscape can recognize the river or mountain even when the drawing is rough. As maps began representing entire cities, that tolerance became more expensive. Walls had to connect. Gates had to appear in the right order. Canals had to cross the correct districts. Now, mapmaking faced a new constraint. How do you preserve not merely the existence of places, but their geometry? The answer required measurement. And one clay tablet from the city of Nippur shows how far ancient surveyors could push that idea. The ancient city of Nippur stood in southern Mesopotamia. During excavations that began in the late 19th century, archaeologists recovered a clay tablet containing a plan of the city. It dates to the Kassite period, roughly the middle of the 2nd millennium BCE. The map labels major features: the temple complex of Ekkur, the Euphrates, canals, city gates, the outer wall. For a long time, scholars could read the names. The harder question was whether the geometry corresponded to the actual buried city. Decades later, University of Chicago archaeologist McGuire Gibson had a chance to test it. The ancient map showed the southern corner of Nippur projecting in a particular way. Gibson's team cut trenches across the corresponding ridge. They found evidence of a city wall more than 14 meters thick. A canal appeared roughly where the tablet placed the Euphrates. Another watercourse matched a branch shown on the ancient plan. An area marked with a word that can mean moat or ponded water corresponded with sediments, indicating standing water. Not every angle lined up perfectly. Gibson explicitly noted inaccuracies in the wall geometry, but enough details matched for excavation geomorphology and philology to support the identification. This is one of the most satisfying moments in the history of mapping. A scribe pressed a city into clay more than 3,000 years ago. Modern archaeologists dug into the ground, and the buried city answered back. The tablet demonstrates that maps had become more than mnemonic sketches. They could preserve a measured spatial structure. That structure could outlive the buildings themselves. But measurement introduces another problem. A city can still be surveyed from the ground. You can walk the wall, count steps, stretch ropes, measure canals. What happens when the map expands beyond anything one surveyor could personally inspect? What happens when you want to draw not one city, but the world? No traveler can walk every road. No official can measure every mountain. No tower is high enough. The map must begin combining reports from people who saw different pieces. At that scale, cartography becomes an act of synthesis. And synthesis forces the mapmaker to decide something maps are still deciding today. Which world should the map preserve? The physical world, as accurately as possible, the political world, the sacred world, the world people imagine beyond the edge of what they know. A Babylonian clay tablet gives a startling answer. All of them. The Babylonian map of the world is small. The surviving clay tablet in the British Museum is only about 12 centimeters high. It dates to roughly the 6th century BCE, though a note indicates that it was copied from an earlier document. At the center is not a scientifically surveyed globe. It is a disk. Babylon appears near the Euphrates. Assyria and other regions are marked. Around the inhabited world runs a circular body of water called the Bitter River. Beyond it sit triangular outer regions. Text on the reverse describes distant places at the limits of human knowledge. To a modern viewer, the obvious temptation is to score the map for accuracy. How close are the shapes to satellite geography? Where are the missing countries? Why is Babylon so important? But that misses what the tablet was doing. The map is a model of a world as Babylonians organized it. Physical geography, political geography, mythic geography, distance, unknown territory, all compressed into one object. This reveals something fundamental. Maps have never been neutral copies of reality. They select, they center, they classify, they tell the reader which relationships matter. A road map exaggerates roads. A subway map bends geography to simplify connections. A political map draws borders that may be invisible on the ground. A weather map ignores buildings and emphasizes pressure. The Babylonian tablet does the same thing in an ancient form. Its world is not wrong because it fails to resemble a satellite photograph. It is answering a different question. Where is Babylon inside the structure of the known and imagined world? That ability to choose a useful structure is what lets maps scale upward. But selection alone cannot solve a larger mathematical problem. The Earth is curved, a tablet is flat, and the farther a map stretches, the more the surface itself begins to fight the representation. At the same time, collecting reports from distant travelers creates inconsistency. One journey says a town is 5 days east, another says 7. One observer measures latitude from a star. Another estimates by road. To combine thousands of places, a mapmaker needs something more stable than drawing skill. He needs coordinates. A place must be able to exist as numbers before it exists as ink. That is the transformation associated most powerfully with a scholar working in Alexandria nearly 2,000 years ago. Claudius Ptolemy lived in Alexandria in the 2nd century CE. His geography did something that changes the logic of mapmaking. It did not simply present pictures of regions, it provided a method for constructing them. Ptolemy gathered geographic knowledge from earlier sources and organized locations through latitude and longitude. Later manuscripts and printed editions preserve coordinates for roughly 8,000 places. He also described methods for projecting the curved Earth onto a flat surface. This is the moment when a map becomes reproducible from data. Imagine the difference. If a map exists only as one drawing copying, it requires copying the drawing. Every copy can introduce distortion. But if Alexandria, Rome, a port and a mountain are stored as positions in a coordinate system, another mapmaker can reconstruct their relationships without ever seeing the original map. The place becomes numerical. A traveler can contribute one location. An astronomer can refine another. A compiler can combine both. The map no longer depends on one person having seen the whole. No one has to. That is how humans finally solve the problem hidden in the title. You cannot see the world from above, so do not try. Measure pieces of it from the ground, give each piece a position, then assemble the positions. Ptolemy's geography contained serious errors. His estimate of the size of the Earth was too small, and many locations inherited inaccuracies from the reports available to him. But the method was more powerful than any individual error. Coordinates separate the map from the mapmaker's body. Projections separate the curved planet from the flat page. Together they make space computable. Centuries later, European printers could produce maps from Ptolemaic coordinates, even though neither the printer nor Ptolemy had personally visited most of the places shown. Modern digital mapping still operates on this principle. The phone does not carry a photograph of the Earth from one impossible viewpoint. It stores layers of coordinates, roads, elevations, boundaries, addresses, satellite observations, and corrections. Then, software constructs the version you need. But mathematical mapping is only one branch of the invention. There is a danger in treating latitude scale and north-up orientation as the final form toward which every culture was naturally progressing. Some of the most sophisticated maps humans created do not look like maps at all. They do not even represent land as their primary information. In the Marshall Islands, navigators mapped something a satellite image barely shows the shape of the ocean itself. A Marshallese navigation chart can look like a loose framework of sticks. Thin strips cross one another, some curve. Cowrie shells may be tied at intersections. There may be no coastline, no north arrow, no scale bar. Yet the object can encode geographic information essential to crossing open ocean. Marshallese navigators developed an extraordinary knowledge of how swells interact with islands and atolls. An island can reflect, refract, and disrupt waves. Those patterns can be felt from a canoe before the land itself becomes visible. In surviving charts, shells may represent islands. Curved strips can represent swells. Other sticks indicate routes or relationships between atolls. Some charts called meadow are closer to regional piloting diagrams. Others known as matang function more like models for teaching how waves behave around land. Here is the detail that breaks the modern idea of a map. These charts were generally not carried at sea as something a navigator checked, like Google Maps. They were studied beforehand. The navigator memorized the relationships, then left the object behind. Once on the ocean, the real navigation happened through stars, waves, wind, and bodily sensation. The map trained the mind. That is almost the reverse of modern GPS. Your phone remembers so that you do not have to. The chart helped a navigator remember, so that the chart did not need to travel. And the geometry was not necessarily to scale. It did not need to be. The purpose was not to reproduce the shape of the Pacific. It was to preserve the invisible relationships that mattered to a canoe. This is why the question, how did humans draw a world they couldn't see from above, contains a hidden assumption. A useful map does not have to imitate what the world would look like from above. Sometimes the important world is not visible from above at all. Ocean swells are experienced through motion. Travel routes are experienced through sequence. A map can preserve those relationships without pretending to be a picture. That insight appears again in a completely different environment. In the Arctic, where coastlines are broken into fjords and islands, one hunter created maps that could be held in the hand. They were not flat. They did not need paper. And when a European explorer encountered them in the 19th century, he realized that the people who made them could describe hundreds of kilometers of coastline they had never drawn in the European way. In the winter of 1884 and 1885, Danish explorer Gustav Holm stayed among Tunumiat communities near Ammassalik on the east coast of Greenland. Holm was trying to map a coastline that Europeans knew poorly. The Tunumiat already knew it intimately. They carried geographic knowledge through travel, memory, conversation, and story. Holm recorded that once local people understood the idea of European charts, they could produce remarkably detailed geographic descriptions. Then, on the 8th of February, 1885, a hunter named Kunit approached him with something different. A piece of driftwood had been carved into the shape of a coastline. Other pieces represented islands and additional stretches of shore. Holm wrote that, Kunit said, making such carvings was not unusual when someone wanted to tell others about places they did not know. That sentence is more important than the object. The wooden map was not necessarily a rugged Arctic navigation device carried through darkness in a mitten, despite a popular modern story. Historical evidence is stronger for another role: communication, storytelling, explaining a journey. The carving gave a listener a coast that could be touched. A fjord became an indentation. A headland became a projection. A sequence of islands became a sequence under the fingers. This is mapping stripped to its cognitive core. Kunit did not need to reproduce the coastline at a uniform scale. He needed another person to understand how the pieces followed one another. The object transferred a spatial model from one mind to another. That is what the Abauntz stone may have done more than 13,000 years earlier. It is what the Nuzi tablet did in clay. It is what Ptolemy did with coordinates. The materials change, the encoding changes. The fundamental act remains: choose relationships, externalize them, teach another mind how to reconstruct the space. But every encoding gains something by losing something else. The wooden coast preserves sequence and shape. It does not preserve every distance. The Marshallese chart preserves swells. It does not preserve a photographic coastline. Ptolemy preserves coordinate relationships. A projection distorts the curved earth to put them on a page. This leads to the final constraint in mapmaking. There is no way to put the entire world onto a smaller surface without choosing what to sacrifice. Every map is therefore a bargain, and one of the most famous maps in history became useful precisely because of the thing it gets wrong. In 1569, Gerard Mercator published the world map associated with the projection that now bears his name. Its great navigational advantage was practical. A sailor following a constant compass bearing could represent that course as a straight line on the chart. To make this work, the projection increasingly stretches the map toward the poles. Directions become easier to use. area becomes badly distorted. Greenland looks far larger relative to Africa than it really is. That is not a failure accidentally hiding inside the map. It is the price of solving a particular problem. And this is the final lesson in the invention of cartography. A map cannot preserve everything. If it preserves angles, it may distort area. If it preserves area shapes, may distort. If it simplifies a subway network, distances bend. If it shows political borders, terrain disappears. If it shows terrain, social relationships may disappear. The mapmaker always asks, what must remain true for the user to succeed? That question connects Mercator to a hunter scratching a river into stone. The materials are different. The scale is absurdly different. The logic is the same. Keep the relationship that matters. Sacrifice the rest. There is even a small fossil of this history inside the English word map. It comes through medieval Latin mappa, from Latin for a cloth, napkin, or towel. The word that now describes a digital model of the planet began with the name of a surface that could carry one. But the surface was never the real invention. Return to the beginning. Your ankle is injured. The hunters are leaving without you. On the stone, the river is only a scratch. The ridges are only lines. The marsh is only a cluster of marks. None of them looks like the real place. That is exactly why the object can work. The real river contains millions of details. The stone keeps one where it goes. The real mountain has trees, shadows, snow, cliffs, smells, sounds, and changing light. The stone keeps one where it stands, relative to the root. The hunters do not need the world. They need the relationships that let them move through it. So, how did humans draw a world they could not see from above? They did not wait for a viewpoint high enough. They built the viewpoint inside the mind. They walked the terrain in fragments, remembered one relationship at a time, measured some, simplified others, encoded them in stone, clay, wood, coordinates, paper, and eventually software. Then they placed all those fragments together on a surface where no human body had ever stood. A map is not a miniature Earth. It is an agreement about what parts of Earth matter. And the impossible view from above was never really a view at all. It was one of humanity's most powerful acts of compression, turning a world too large to see into a pattern small enough to share.